All right, good morning, everyone. So we're going to go ahead and get started. Um, First of all, thank you all for joining today's Research Radar webinar, Steer, Step, and Cycle, Safer by the Mile, hosted by Minnesota Department of Transportation and the Minnesota Local Road Research Board. My name is Molly Yang, and we're excited to have our presenters, Ali Razakani, Michael Levine, Mark Waziski, and Renee Keogh with us today. So today's webinar is part of the Research Radar series sponsored by the MnDOT Office of Research and Innovation and the Local Road Research Board. Each month, we like to highlight different research projects focused around a common theme. And before we get started, I'd like to read the Tennyson warning. This session will be recorded for those who cannot attend. If you have enabled your camera during the session, the recording may include your image, which is private data under the Minnesota Government Data Practices Act. You are not required to allow MnDOT to use your image, and there are no consequences for declining to do so. To opt out of the recording, you may simply turn off your camera. So MnDOT's Office of Research and Innovation manages over 185 research projects in progress that range from local initiatives to pool fund projects with other states, comprising both basic and applied research. We're here to help transportation practitioners determine whether new research is needed or if existing studies may solve your needs, recommend the best research methodology for your project, access local and national funding sources, and also manage your project from start to finish. And our partner, the Local Road Research Board, is a city and county run organization that sponsors research and educational initiatives that address local transportation needs. So you can stay up to date with us by following us online and subscribing to our newsletters. We will also send you website and subscription links in a follow-up email after today's webinar. So for 2026, we funded 28 new academic research projects. You can scan the QR code on the screen to view the full list. If you have any subject matter expertise and are interested in serving on the technical advisory panel, you can reach out to our office by emailing research.dot@state.mn.us. And again, this will also all be sent out in the follow-up email. And now I'd like to introduce our presenters. So presenting on designing an autonomous service to cover transit last mile in low density areas, we have Ali Reza Khani. Ali Reza Khani is a professor of transportation systems engineering at the University of Minnesota Twin Cities. His research focuses on multimodal transportation network modeling, transportation data analytics, and sustainable transportation systems. Dr. Khani has served as principal investigator on numerous research projects for the Minnesota Department of Transportation and the Local Road Research Board, alongside extensive research initiatives funded by federal agencies. Up next, we have mobile device data, non-motorized traffic monitoring, and estimation of annual average daily bicyclist and pedestrian flows. We have Michael Levine. Michael is an associate professor of transportation engineering at the University of Minnesota, focusing on using operations research tools to solve network modeling and optimization problems. And lastly, on crash benefit of non-motorized facilities, we have Mark Waziski. Mark's passion and dedication for public works started early, from riding in the plow truck with his dad to watching sanitary sewer inspection videos for fun. His goal is to live the state aid mission every day by providing world-class customer service with a smile. And joining him, we also have Renee Keogh. Renee is Senior Director with SRF Consulting Group in Minneapolis and has more than 25 years of traffic, transportation safety, and transportation research experience. For the last decade, she has worked with the Local Road Research Board on transportation safety related research for local agencies. And with that, I'll pass it on to Dr. Khani to get us started.
Thank you, Molly. I'm going to share my screen. Can you see my screen now?
Yes, I can.
Okay, great. Thanks for the invitation to present in this webinar. So if you notice, the title of my slides are slightly different than what has been advertised in the webinar, but it's the same project funded by local road research board. This is the same content, designing autonomous mobility on-demand system for covering the last mile transit gap. Uh, the the research need came from the fact that fixed route transit service in rural areas, in low density, smaller urban areas, they have gaps, they are sparse, and they have long headways. Therefore, they're less attractive compared to other modes of transportation. And this leads to more people using personal vehicles, therefore, increased vehicle ownership and vehicle miles traveled, and all the consequences of that. There are different policies and technologies that can improve transit, make it more attractive, and reduce the vehicle miles traveled. And particularly in this project, we look at the autonomous mobility on-demand system that has more efficient fleet repositioning and demand responsiveness. And the hypothesis or the question was that can AMOD be integrated with fixed route transit to fill the first mile, last mile transit gap and attract more people to transit services? Um, and therefore, the need was for analytical methods to be able to design and evaluate such an AMOD system to inform multimodal planning and policy. I will talk a little bit more about the specifics of the autonomous mobility on-demand system in future slides. But this is the research need of the project. Um, Early in the project, we identified a case study for testing, for numerical and simulation testing of what we are proposing. Um, I should clarify that what we develop and investigate in this project is not unique to this case study, but this is only for the purpose of illustration with simulation methods. So this is the Miller Hill Mall area in Duluth, a big commercial area with a lot of retailers, big parking lots, a mall, and a few other shopping plazas along a major highway. The transit routes in the Duluth bring people from the residential areas to the commercial areas quite efficiently up to the mall area. But when it gets to the mall area, the transit routes zigzag through the parking lots and they have some stops, but they do not really serve every single store. Therefore, people who use transit to go to the mall area, they may have to walk a long distance to get to the store that they want to do shopping at, or they may have to cross multiple streets, and it causes inconvenience and safety risk for transit users. And then if you look at the number of people who use transit to go to the mall area, this is the same map, just 90 degrees rotated. These circles show the number of passengers that are using each stop. Each circle is a stop. And the number of passengers using each stop is divided by the number of boardings and alighting. And we see an asymmetric pattern of how stops being used, which is normal depending on where they are located and what side of the street, what direction they are. But if you look at the aggregate level, boardings and alighting in the mall area, we see a mismatch between the boardings and alighting. There are more alightings in the mall area, meaning that more people are using transit to get to the mall area, but there are fewer boardings, meaning that some of the people who use transit to get to the mall area do not use transit for going back to their home location. And this may be an indicator that transit is less convenient for them or less available to them for their return trip, or maybe they use other modes of transportation after they do shopping with all this stuff in their hand. Therefore, there may be a mismatch in the transit service in the mall area, not regionally. I'm clarifying that this is only the local gap in terms of transit. But now let's look at the mobility on demand system and how it can address this issue. We are looking at two technologies here. One of them is autonomous vehicle, and the other one is mobility on demand system. Autonomous vehicles, many of us are familiar with it, and there are different levels of autonomy. The lowest levels are basically the cars that are available in the market now, the new cars that are sold now with adaptive cruise control, lane departure assist, and things like that. But at full autonomy, autonomous vehicles would not need drivers, and they can navigate themselves. They can go from A to B without needing a driver. We are looking at that kind of autonomous vehicles in our study. Mobility on demand system is a system where passengers can request a ride on their smartphone app and then be picked up and dropped off at their location, a kind of a curb-to-curb service available in real time. Combining these two provides the autonomous mobility on demand system that does not need a driver, and it kind of addresses the agency's challenge of driver shortage. So that can be an added benefit of autonomous mobility on demand systems. It can be more responsive to demand, and it can be suitable for local transportation, for example, first and last mile services. And also, studies show that it can be more cost effective. A study in Switzerland a few years ago looked at different modes of transportation and cost per passenger mile. By looking at the study and converting the numbers to the US dollars and accounting for inflation, we came up with the numbers of 66 cents per passenger mile is the cost of providing autonomous mobility on demand service, as opposed to $4.37 per passenger mile for a regular taxi or a human-driven kind of on-demand mobility services. And the big cost gap is primarily because of the driver wages that can be removed from the operational cost. So with this mobility on-demand systems that we are envisioning, the question is how it can be integrated with the fixed route transit in the Miller Hill Mall area to provide a better and more convenient kind of mobility option to the passengers. So the integration of mobility on demand system with fixed route transit provides this multimodal trip itinerary, and people from their origin anywhere in residential areas in the Duluth region, they can use transit, fixed route transit, to get to the Miller Hill Mall transit hub. What is this transit hub? This is a location that we have identified close to the Miller Hill Mall area, the whole commercial area, where all the fixed route buses will terminate their service there, and it can be a hub. And then the passengers get off the buses at that point and use MnDOT to go to their final destination that can be any of the stores in the commercial area. So therefore, there's a seamless transfer between fixed route transit, maybe another fixed route transit, as you know, transfers are inevitable in any transit services. But then the last part will be served by autonomous mobility on demand system. We developed optimization algorithms with a lot of equations and mathematical derivations that I'm not showing in this presentation, but are available in the reports and the papers that we published. But I'm going to show the simulation study in this presentation. So we developed this multimodal transportation option, and we integrated with a regional mode choice model to see first how much transit can be improved by providing this last mile access, and second, how much demand can be attracted to the transit service after introducing the last mile service. So we conducted the simulation analysis with the specification shown on this slide. We looked at the 2-hour afternoon peak period on a Friday, because Friday has the highest demand of the travel to the mall area. And we used the cell phone-based travel data provided to us. And we estimated that about 140 passengers use transit to go to the mall area within that 2-hour afternoon peak. And this is about 1% of the total trips to the mall area. So only 1% of people currently use transit to go to the mall area. And with the mathematical derivations that I'm not showing here, we calculated that to serve that level of demand, we need minimum 13 autonomous vehicles as part of our mobility on demand system for the last mile transit. We developed scenarios with that minimum fleet size and also with 1.5, 2, and 2.5 times the fleet size to see how the service will improve if we provide additional service with higher levels of fleets. In the next few slides, I'm going to show some of the summary of the results. The first thing is the service quality, the MnDOT service quality. And remember that this is part of the multimodal trip itinerary, the fixed route transit bringing people to the transit hub next to the mall area, and then MnDOT taking people from the hub to the final destination, and vice versa. After people do shopping at one store, they can use the MnDOT to go another shopping, maybe across the street, or after they are done, they can use MnDOT to go back to the transit hub, and the transit hub, at the transit hub, they can use the fixed route transit to go back to their origin. initial origin home location, basically. So this graph shows the average waiting time or distribution of waiting time of passengers for the AMOD service. And the left box basically shows the results for the minimum fleet size, 13 vehicles in the service. And it shows that the waiting time of passengers is mostly between 1 to 3 minutes, which is very reasonable. If you compare it with 15-minute bus headway or 30 minutes bus headway, this is a very reasonable waiting time, and it's on average 2 minutes. As we increase the fleet size slightly, we can see that the waiting time can decrease significantly to a point where a waiting time can be less than 1 minute or virtually zero, which means that people can be picked up almost instantaneously as soon as they request a ride. That's a very reasonable and very high quality of service in terms of the waiting time. And that improved quality of service could lead to increased transit demand. Remember that our estimate was that only 1% of people use transit to go to the mall area, but our simulation shows that as we introduce the AMOD service with the minimum fleet size, the mode share of transit would increase from 1% to about 1.5%. Again, in terms of the absolute numbers, it may not be a lot of transit trips, maybe going from 140 passengers per peak period to about more than 200 people. But this is a huge percentage-wise increase. It's about 50% increase. As we increase more fleet size in the AMOD, we see that the transit demand will increase. So as we improve the quality of service with more AMOD, we can see that more passengers are attracted to the transit service. And that could lead to more VMT saving. By providing the AMOD in the system, of course, we are adding some additional VMT because there are additional vehicles in the system that move around and transport passengers. But that encourages some people to get out of their personal vehicles for the longer trip to the mall area and use transit to get to the mall area and then be served by AMOD in the last part of it. Therefore, collectively, the introduction of AMOD leads to some VMT saving or net saving because there's an additional VMT and there's a reduction of VMT by personal vehicles. The net amount is a notable positive number, VMT saving, which is another advantage of the introduction of AMOD into the transit system. But also looking at the AMOD operation itself, because one of the contributions of this research was how to design, control the AMOD system. The challenges are real-time dispatching and assignment of vehicles to passengers and also repositioning of the empty autonomous vehicles to go to places where there is higher demand. So that we developed an optimization algorithm that does this real-time dispatching and rebalancing to minimize the operational cost of the AMOD system. And the graph shows on the left, it shows the number of customer carrying vehicles, basically in-service trips that autonomous vehicles make. And this is linearly increasing as we introduce more fleet size. This is primarily because there will be more people using the AMOD service. Therefore, there will be more in-service operation, which is not a bad thing because they're serving people. On the right, the graph shows the number of rebalancing or empty repositioning vehicles. And thanks to our optimization algorithm, we see in most of the cases, the repositioning trips is very small compared to the in-service operation. And as the system becomes bigger, more fleet, more passengers, there's a little bit of repositioning, but that's still much less than the in-service trips that autonomous vehicles make. So in summary, we studied this AMOD service and we developed algorithms for optimizing the operation and integration with the fixed route transit service for the Miller Hill Mall area as a case study. Again, this can be applied to other cases. This is a general optimization and simulation model, just only illustrated for the Miller Hill Mall area. Through our simulation experiments, we found that the AMOD can be an efficient transit service suitable for first and last mile access to fixed route transit. It can improve the quality of service and attract more riders to the transit system. and it can reduce the VMT in the region. The net effect of introduction of AMOD is a net VMT saving in the region. A few recommendations for future studies and the next steps. One of the assumptions in this study was about the parameters of choices that people make in terms of using AMOD, using transit, or using personal vehicles. There could be more studies on understanding people's attitudes toward autonomous vehicles and their choice parameters and a perception of a riding autonomous vehicle compared to transit and personal vehicle. This could be done with different surveys and interviews with people. This study shows the application in one local area, but you can imagine that there may be multiple local pockets that can be served by autonomous vehicles, and autonomous vehicles be integrated with fixed route transit. By introducing these services locally at different places, there can be a collective net effect of improving the quality of service for transit and reducing the VMT. That can be a full-scale application of AMOD in a region. It is very likely that autonomous vehicles are also electric. That means that they need to go back to charging. They have limited range. They need charging stops and so on. So studying electric vehicles as part of AMOD is another next step that we already studied. That we actually we have we continued this research by studying the electric AMOD, but that's not part of this research and presentation, and I'm happy to share that offline if anyone is interested in that. And the last step, the recommendation to the local agency was that to do some sort of pilot testing, either with full autonomous vehicles that could be a little bit costly and challenging, but also with actual drivers that can mimic the behavior of an autonomous mobility on-demand system, even though there are drivers driving the vehicles, but the decision, dispatching, and repositioning could follow the optimization algorithm that we developed to see how well it can perform in real world, actually. I'd like to acknowledge the sponsors and collaborators of this project, and also my former students who were research assistants working on this project. Thank you very much, and I'm happy to answer questions, I think, at the end of the session.
Thank you. All right, and I think we'll transition over to Michael. So whenever you're ready.
Great. I will share my screen. Okay, can everyone see my screen?
Yes.
Awesome, thank you. So thank you for attending today. I'm happy to talk about a project I did with for Minnesota DOT, looking at how we can estimate the flow of or volumes of pedestrians and bicyclists on individual links using mobile source data. So fundamentally, the problem that we want to solve is that a lot of our designs, our plannings, models, or decisions are made on annual average daily traffic, right? Like how many people are walking or cycling or driving along a certain bike trail or road per year, right? Or on average per day. And there are various reasons you'd want to do this. Like, for example, looking at highway safety manual, we need pedestrian volumes to estimate intersection safety, right? The problem here is that actually getting these estimates of how many people are using a road or AEDT, that's actually can be quite difficult to obtain. Now, we can definitely predict it using some travel behavior model, but getting travel behavior for pedestrians and cyclists, that's itself a difficult problem. You might need to get some surveys. Travel behavior inventory is one possible source, but it doesn't capture everything. The other option would be trying to measure it directly using some sort of sensors, and MnDOT and local agencies do that to some extent, but it's limited, right? Like these sensors are kind of expensive. We don't have them everywhere. I think MnDOT had like roughly 140 across the metro area of Minneapolis, St. Paul. So, considering that there are probably 10,000 or more individual segments that you might want to know how many people are walking or cycling, this is very small, right? So we need to do something very different than just relying on sensors or surveys. And the idea here is we could use mobile source data. People, I mean, most adults have smartphones now. These smartphones are generally have navigation on, and various companies are collecting this data and making it available. So MnDOT subscribes to Streetlight, or at least they have been for the past few years. There's also sources like Strava that people use these to track their workouts or their exercise. There are various different mobile source data that aim to provide things like the volume of people walking or cycling along a link, like a trail or a path, and also streetlights and some other sources will provide origin destination trips. So, like how many people are traveling from one uh, broad traffic analysis zone to another TAZ. The problem, of course, as you can probably imagine, is that mobile source data does not capture everyone. There are a lot of people who don't have smartphones. Maybe their location's turned off. Maybe they have privacy settings. Whatever. They're not being captured at all. It's that their locations, especially like rural areas where GPS is not great, service is not great, and so they're not being captured. And of course, if you rely on things like Strava, it's only the subset of people that are using Strava app, which tends to be demographically more white people, more higher socioeconomic status, or missing a lot of groups. So these are all problems that if we want to just rely on mobile source data and report that, we're going to miss a lot of things. And also, actually, if you look at a mobile source data, there are oftentimes gaps, like some edges or some links are just completely ignored. Sometimes there's some days where there's just missing data. And these are all things that if we want to estimate annual daily traffic, it's going to be a problem. So what we want to do conceptually is combine several sources of mobile station data, both Streetlight and Strava, and also combine them with a model of how travelers behave. The idea is by combining origin destination trips with some model of route choices of where people would which routes people would take to go from their origin to destination, and getting the link volumes along every link from Strava, whereas they have origin destination data from Streetlight. We can combine these three different sources of data, the model and two mobile data sources, and use that to try to reduce the errors here. So I'm going to talk about the methodology. It's going to be a bit of math, so I'll kind of skip over the math, but I'll just point out enough of like so you can get the idea of what's going on, and then I'll show some results of how this might be effective. Um, Starting off, a lot of notation here, but the main thing that I just want to summarize are what the input data that we need are. First, we need to have all of the links that we're trying to consider in a network, as well as where they're connected to each other. So, for example, if we look at an intersection, we need to look at the incoming and outgoing links or segments of trails, roads where people could bike on or walk or walk on. We also need to know the number of people who are leaving a location and number of people going to a location, normally known as productions and attractions in like a trip distribution modeling sense. And then we want to have some estimate of the volumes from mobile source data. I'm going to call this X tilde to indicate that it's not the correct number. It's just a what we're getting from the mobile source data directly. What we want to do, of course, is estimate the actual traffic volumes, which if we're observing like 100 people, we know that there's at least 100 people on this road or this bike trail, but there could be a lot more, and we could be missing some. So what we want to do is kind of just to summarize the steps. We want to figure out a route choice model. And it's going to look complicated, but fundamentally, it's kind of like a logit model, like a discrete choice model you might use for mode choices, except instead of for like choosing between taking a bus or taking a car, what we're really choosing between is which path are you taking, right? And these should depend on things like utility, which for cycling, the utility might be based on like what's your travel time. It could be based on things like bike lanes or other characteristics, but it's fundamentally a utility function, and people don't always take the shortest route, but the probability that route is taken is based on that utility. Um, what we're going to do then is try to have like a least squares estimation problem, kind of like a regression model. Like if you're trying to create a linear regression, that's like minimizing the sum of squared errors. So we're trying to do the same thing here. Then we're going to use that to use that to get some estimation of link volumes. We're going to do a final sanity check on that, which I'll explain, and then we'll have some results on the prediction. I think that's very abstract, so I thought it's probably helpful to start off with a simple example of what this looks like. So you can see with this very simple network, we have a lot of useful information. And this kind of illustrates the inputs that we're getting. So first off, we have the network structure, which is that there are 4 nodes and that some of them are collected by links. I've made them directed links, so they're only going one direction. So you can think of like a bike lane that you're only traveling one direction. And we also have productions and attractions, meaning that there are 100 people leaving node 1, 100 people going to node 4. And because there aren't any people going to nodes 2 or 3 in this example, we know that all 100 people are going from node 1 to node 4. Finally, we can observe, let's say we observe one of these links from 1 to 3, we observe a volume of 40 travelers. So you can look at this example and say like, well, there's a lot of missing information. We want to know how many people are using links 1 to 2, 2 to 4, and 3 to 4. Do we have enough information for that? And the answer is definitely yes, actually, because if we know 40 people are going from node 1 to node 3, that means those 40 people to get to node 4 also have to be going from node 3 to node 4, which means that if there are 100 people total going from node 1 to node 4, we have 60 people going on the bottom route 1 to 2 to 4. So from this limited information, we can immediately actually get the unique solution to this problem of estimating all the link flows. And obviously this is very simplified, but that's kind of an illustration of what we're trying to do conceptually. To make it more realistic, let's consider the same problem, except now I've added another path going through the middle, nodes 1 to 5 and then 5 to 4. So now there are 3 paths. We have the same scenario of 100 people going from node 1 to node 4 and 40 people from node 1 to node 3. But now you can see that we can't directly estimate. We can estimate that there are 40 people going from node 1 to node 3 to node 4, the top path, but we don't know of the remaining 60 people how many of them are going on the middle or the bottom paths, because we don't have any flow information to estimate that. So what we want to do instead is look at the routes and say, well, maybe the middle path is shorter, so we can predict more people going on a middle path than a bottom path. Something like that. That's kind of how we would incorporate route choice here. And of course, in the real network, there are a lot more than 2 nodes for productions and tractions. There's a lot more interesting interactions there. But fundamentally, that kind of shows how we can break down the problem, use partial information to estimate things. Okay, so going down to the route choice, the idea is we want to assign the trips that we don't observe onto the shortest path, because a lot of these edges just aren't observed from open source data, and also we're missing some of the people, so we want to try to estimate this anyways. But if you look at pedestrians and cyclists, there are often going to be many paths with equal or very close travel time. Just imagine like walking around a block. You can walk like up and to the right versus like to the right and then up. It's like there are multiple paths. It's probably going to have the same distance and the same travel time. So we're going to see people split their routes, and that's why you need some kind of logit model or some kind of model for like saying what's the probability of taking each route. What we're using is a standard logit model. There's some math behind it. I'm not going to go through all the math just because this is fairly standard and also kind of technical. So the main idea here is we're estimating the probability of taking each route using the utilities. What this ends up having is we're trying to get a prediction for how many people use the link volume, which is node X, and it turns into a combination of trips travelers going from origin to destination times the probability of them using a specific link for people from going from specific origin to destination. That's useful because this gives us essentially a formula that says if we want to get link volumes, I can decompose it in terms of origin destination trips. And if you recall, that's something that we have some way of estimating from Streetlight is the origin productions, destination attractions. So what we're doing is going to be using a sort of constraints that says, okay, we want to minimize sum squared errors here. And the sum squared errors is our prediction, which is based on a logit model, minus the observed from Strava. And we're going to enforce the constraints that if we look at Streetlight, we know how many people are leaving an origin, we know how many people are going to destination. That's going to have certain constraints on how many people travel from one origin to one destination, which affects our prediction of the link flows. So this is kind of like similar to like a linear regression problem, but more complicated to solve. But it's kind of the same idea as that you're trying to minimize sum of squared errors here. The way to solve this, we used a customized gradient descent algorithm. If you remember from calculus, if you travel along the gradient, that will tell you the direction to find where the function increases or decreases. So we want to make the sum of squared errors decrease, and we just want to keep going in that direction. It's multivariable, so it's a little more complicated than that, but that's kind of the idea, is that you just want to keep finding the direction of decrease and then going in that direction. There's one more thing though with flow sanity, because one thing you end up with when you're doing sum of squared errors, you actually there's no reason that your predicted flows have to be greater than observed flows, right? It's possible that he predicts something less than observed, and that could still have a small sum of squared errors. But with multiple source data, the fact is, if you're observing someone there, then someone actually is there. In other words, multiple source data is really a lower bound. It's not just a estimate; it's actually a lower bound on how many people are traveling there. So we do a final sanity check, which is trying to ensure that the predictions we're getting are lower bound or are respecting lower bound from multiple source data. And then to do that, we have to ensure flow conservation to make sure that the people that go on a link actually end up going somewhere else to get to your origin destination. So that helps improve the estimation slightly by respecting the lower bound of multiple source data. Okay, so it's kind of complicated. I think what I really want to do is show like some numerical results of what this looks like. So first off, we're going to try a very simple toy network structure. The reason I'm just showing this to you is because we can actually write down everything that we're given. It's complicated enough that we have two origins, two destinations, we have various links. It's complicated enough that you can't just solve this by inspection, but it's simple enough that I can write down the matrix of like the origin destination traveling as like this 4x4 matrix. And the goal is here, what we're going to do is show here are the observed link flow counts. So there are 3 links that we don't have any data for. There's some links that we just know are 0, and then there are 3 links that we have some data for. So the negative ones indicate where we don't have any data. So that's what we want to fill in through this estimation. And when we do this estimation, you can see we get good numbers for the 3 links where we didn't have any information. And then the 3 links that we had information, our estimation basically predicts or re-estimates what we observed in the first place. So what we're essentially doing here is we're filling in missing data by using the network structure. This just shows basically that we're solving the sum of squared errors. So like as the iteration goes, gets higher, our sum of squared errors gets lower, which means that we're finding a good solution here. Okay, so that's just a toy example to show what this algorithm is doing. What we did that's probably more interesting to you is we did this on the entire Minneapolis-St. Paul metro area. And actually this area has more than 1 million links. They were all found with OpenStreetMaps. Some of these links have data available from Strava. Some of them don't. we also had to divide this into multiple smaller subnetworks because we couldn't process this all at the same time. But the important thing is looking at this snapshot of the map, you can kind of see things that numbers that make sense. So brighter colors like white or yellow indicate higher flows. Lower, darker colors like the red indicate lower volumes. And so like you can see like out in the suburban areas, we see a lot of red, not so many pedestrian cyclist volumes there, whereas in the CBD, we see a lot more yellow. So we're seeing a lot more people there. And that's kind of intuitively makes sense. So we have this map online, so it's like you can actually click on individual locations, zoom in, and see what the pedestrian cyclist volume predictions are there. But it can show in the slides, so this is just the main overall prediction here. But you might of course ask like, okay, yeah, the numbers make sense, but how do we know they're actually right? So that was something we tried to do some work on. What we did was we looked at various locations and we decided to go out and count them. So we had an undergrad go out and just watch locations for a few hours and count the number of people there, and then from there try to extrapolate how many people are traveling per day on average. And what we have here are these graphs that compare. The blue is the estimate, the orange is the count that we're showing. So you can see that there's like some locations where the count is higher. There's some locations where it's lower, but most of them, they're pretty close. So it's kind of nice that we're not like super far off from what we counted. So the main conclusion here is that we have this method that incorporates mobile source data with a network structure to improve on something that we can't get with either one alone, right? We can't get good estimates just with mobile source data alone, but we can't get good estimates with the network structure alone either because you don't get inputs, but by combining them, we can get a lot more predictions on where people are cycling and walking. And this is really nice just because there's not that much data that we can collect with physical sensors. And so now we have a lot more data on where people are walking and biking. I mean, sure, mobile source data has its issues. This is not perfectly accurate count, but it's a lot better than having nothing. There are various methodological conclusions as well that this is not a trivial problem, but the main idea is that we have good estimates for pretty much all links in the network now. Happy to answer questions, I think, at the end, or you can email me, but thank you for attending.
Thank you, Michael. Looks like there might be some connectivity issues with glitching, voice glitching, and also presentation. So either Renee or Mark, I'll have you share, and if there's any blurriness, I can share on my end. Hopefully that can resolve those issues.
Sounds great. So I'll jump into it. Thanks for the opportunity. Again, I'm Mark Fizicki, the State Aid Operations Engineer, and we are here to talk about crash benefits of non-motorized facilities. This one parallels another study that I was working on, which is the impact of design standards related to speed. I'll pop that one in the chat at the very end to not distract from our presentation today. So Renee and I will take us through our research findings for this project. Next slide, please, Renee. So what we're going to talk about is why this study matters, the project approach that we used, methods for consideration, why analysis became impractical, some major roadblocks, the Minnesota data and what it shows us, national and statewide findings, what are some other evidence says about facility effectiveness, and then we'll wrap it up with some conclusions and recommendations. Next slide, please. All right, so what did we do and how did we go about it? So we were interested in finding walking and biking facilities and additional information about them as they continue to grow across the state and nation. And that goal was to understand data-driven needs to provide guidance around treatments to improve safety across the entire system. The study aimed to estimate safety benefits of non-motorized facilities using Minnesota crash data. The facilities we focused on were sidewalks, shared roadways, striped bike lanes, separated bike lanes, and lead pedestrian intervals, or LPIs. So our project process and approach, we started by putting together a technical panel, which that began in October of 23. The goal overall or underlying theme was to develop a Minnesota specific crash modification factor, or CMF. And why we wanted to do that is we believe that user behavior varies by region, that national values may not reflect the Minnesota context, and the need for findings should be grounded in local roadways, behaviors, and geographic conditions. The figure that's there shows some of the underlying reason why we targeted that. Again, Minnesota shown as having a very low pedestrian fatality rate by population in comparison to the rest of the US. So we moved forward with using two methods of development, both a before-after analysis and a cross-sectional study. And I will turn it over to Renee, and she will talk us through some of those details.
Great, thanks, Mark. Like Mark said, we looked at two different methods to do this analysis. So originally we thought we were going to do a before-after analysis, which is what it sounds like. You pick a location where, let's say, a bike lane was installed, you look at crash data before and after and see if there's been a reduction. This requires finding many sites that have the similar characteristics and also robust crash history. So when we were digging into doing this approach, we realized that finding similar sites and also a lot of crash data was quite limiting. So we decided to look at another approach, which is called cross-sectional analysis, which essentially takes a site that has a facility and compares it to a site without that same facility during the same time period and has the same controls such as roadway type, vehicle speed, volume, and lane count to see if there's a difference in crashes in those locations. So when we started kind of digging into how we were going to do this analysis, we started looking at how many scenarios we were going to have to look at. If you could look at this table here, on the left lists all the strategies that Mark talked about that we were going to look at. So if there's a sidewalk present, different bike lane types, and then the leading pedestrian interval, as well as locations that don't have those strategies. And we started calculating if we're looking for a bike lane, we need to find locations with a bike lane that have 2 lanes and 3 lanes and 4 lanes. And so the number of lanes scenarios was up to 4. And then there could be different speed ranges on these roads. So there could be like 4 different speed ranges we could look at. And then there are a number of ADT ranges we could look at. And so when we started like laying out number of scenarios and that expedited, we're up to 64 different scenarios per strategy. And for each strategy, we wanted to look at 10 locations and then 10 years of crash data before and after, which brought us up to over 6,000 years of crash data needed per site, and overall over 50,000 years of crash data. And when I say years, it's just looking at by site the before and after years. So this really, when we dug in and looked at this table, we kind of paused and we were like, this is probably more than we can chew based on the project that we had scoped. We don't have the budget to look at all these scenarios. So how are we going to move forward? So as a group, Mark said we worked with a technical advisory panel that was all ped bike professionals, and we were talking about, well, how do we move forward and do some of this analysis? So we paused on figuring out the scenarios, and also one of the challenges we had was figuring out locations where these strategies existed and locations where they did not exist that we could use for this comparison that had the same context of number of lanes, speed, and ADT. So we paused and we decided, well, let's look at the crash data to see how many ped bike crashes are out there that are going to help us with this analysis. So then as we were going down that route, we ran into a couple other roadblocks. So the first is there are too few target crashes for us to use in this analysis. So some numbers, we dug into the numbers of like how many ped bike crashes are happening across the state. And we focused in on municipal urban areas specifically. So just for example, some numbers for you. When we looked at all crashes that occurred in a municipal urban area over a 5-year period, there was about 111,000 crashes. Now that includes everything, vehicles, ped bikes, all severities, that's all crashes. If we break that down and look at crashes that are just ped bike crashes in those same spaces, we're at 5,000 ped bike related crashes. And that is any level of severity. If someone was, had no injuries up to if there was a fatality. And then a lot of times in the traffic safety world, we really like to focus on the severe crashes, one where someone has a life-changing injury or there's a fatality, to try to eliminate those. And so when we look at severe crashes, there were 700 severe ped bike crashes over the 5-year period. So when you think about 700 across the entire state of Minnesota, the likelihood of one location having more than one severe ped bike crash is pretty limited. So we when we started digging into the data, we realized even if we did all those different scenarios that we talked about, the crash data really isn't going to be there to give us a significant information about the effectiveness of the strategies, especially when we're looking at just the ped bike crashes. We also are looking at exposure data, so trying to understand how many ped bikes are out there. So this kind of goes back to the presentation Michael just gave about, there's not as much reliable ped bike count data out there. And so that makes it hard for us to evaluate risk and calculate crash rates. And then from there, finding the locations, like I mentioned, was challenging. People avoid unsafe locations, and low usage can make risky areas appear safe when really they might not be safe, and people just aren't using those locations. A little bit more about what the crash data showed us. So when we were looking at the statewide data, about 2% of all crashes in the 5-year range we looked at involved a ped or a bike. And of those, 14% were fatal crashes with a ped or a bike. 60% or more of severe crashes, again, that's fatal and severe injury crashes, occurred at intersections. And 72% of bike and ped fatalities occurred in urban areas. So some key kind of system trends that we identified was that nearly half of severe ped bike intersection crashes were at signalized intersections. The majority of ped bike crashes occurred on city systems. And that's all bike crashes, not just severe. And then when we look at fatalities, over a third happened on county systems, and that severe crash densities on city streets are 3 times higher than state highways. So some of these things seem intuitive and something that you maybe could have come up with on your own, but now we have the data to show that this is, where these type of crashes are happening. We want to look at national versus statewide findings. So some of the national findings we found were that most ped bike crashes occur at non-intersections. Fatal crashes often happen in dark and unlit conditions, and that the highest risk time period is from 6 to 11 p.m. When we looked at Minnesota patterns, and this data is from the Minnesota VRU study, the Vulnerable Roadway Users Safety Analysis, the crash concentrations on high activity corridors, particularly on minor arterials, and there's a high frequency of Twin City metro area crashes, often associated with low income, higher proportions of people of color, and places with pedestrian oriented land uses. Now there is national data about the effectiveness of these strategies, and we knew that going into this study, but like Mark mentioned, there are differences based on context and regions that we were hoping to dial in and get a little bit more specific crash reduction rates for Minnesota situations. So there is information out there that we can use for crash reductions at the national level. So our conclusions are that while we weren't able to complete the study as we had hoped and come up with Minnesota-specific crash modification factors, we did realize some of the barriers. So crash data is sparse when it comes to ped bikes specifically. Ped bike volume data is sparse as well. And trying to find sites that are comparable to each other in urban areas is quite challenging when you're trying to find locations with the same number of lanes and speeds and ADTs. So what this means for agencies is that non-motorized facilities still matter for safety, mobility, and accessibility, that low use may reflect latent demand and not low needs. So just because people aren't using a road doesn't mean that there isn't a need for some of these non-motorized strategies. And the agencies should select countermeasures based on context, user needs, and desired safety outcomes. And I would say some of the findings that we shared in our report about where ped bike crashes are occurring and what type of context should be helpful in directing agencies on where they should consider implementing these strategies as well. That's it.
Awesome. Well, thank you so much, Renee and Mark, for wrapping us up with our presentations for today. And so now we are going to transition to our Q&A session. Feel free to come off of mute, raise your hand, unmute yourselves, and ask your questions verbally. But I am seeing some questions in the chat, and so I will just be going in order and referring to the presentation that the question is on. And so first question we have from Kessa, and this is for Ali Reza, in reference to the AMOD wait time. So Kessa says 4 minutes, while the highest on the chart is still a really short waiting time compared to fixed route transit. Did you consider a smaller minimum fleet size? Or alternatively, why did you set 13 as the minimum?
Yeah, thank you for asking this question. So I didn't show all the mathematical derivations and the modeling methodology of the study, and I'm happy to provide that in the report and in the paper. But the bottom line is that given a few inputs, including the demand and the network topology and a few other parameters, we did a mathematical derivation and calculated what is the minimum fleet size needed to be able to serve the demand without the system going to the super congested or unstable situation. That minimum is the absolute minimum. And anything more than that would be a design choice. So with that minimum, our simulation shows that most of the waiting times are between 1 to 3 or 1 to 4 minutes, with average of 2 minutes. But note that this is the average, or this is the 25 percentile to 75 percentile. There may be cases that are more than that, but majority of the waiting times are within like 3 to 4 minutes. Again, and another thing is to consider that this is a pretty small geographic area, and these vehicles are serving people for probably less than a mile. So they can go back and forth quickly and serve passengers. So the simulation results show that the average waiting time is 2 to 3 minutes, and I think this is realistic. I mean, even with Uber and Lyft that we use, in urban areas, larger urban areas, typically we can get a ride within like 5 minutes or so. I don't think this is super unrealistic, but again, this is subject to a lot of parameters in the simulation. I hope I answered the question.
Great. Thanks, Kessa, for your question. We have another question from Esther. Does the AMOD fleet size consider a percentage of vehicles under maintenance?
It does not. It just assumes the number of vehicles in service. However, those vehicles in service at any point in time, some of them may be carrying passengers, some of them may be repositioning to other areas where the demand is. So there is a proportion of them that are in an empty repositioning situation, but no consideration of backup vehicles for maintenance or other things.
And then also for Alireza, a question from Aiden. Do AMODs only transfer from the hub to the mall and back? I thought one initial finding in the study was that people didn't want to use the bus on the way home. So could people use AMOD to get all the way home?
The short answer is no, and the idea is not to replace the fixed route transit with AMOD. I mean, the fixed route transit provides the huge benefit of multiple people sharing a bus and reducing the VMT on our network. The AMOD is here to fill the gap. You know, the fixed route transit provides a service for the longer part of the trip, but in the last part or the first part, there may be inconvenience of walking to the bus stop or walking from where bus stop where you get off the bus and to the final destination. That inconvenience may be perceived even more negatively by people, and therefore it make people not using transit. The goal here is to make that inconvenient part of the transit trip more convenient by providing AMOD service. Otherwise, if you were to replace the buses with AMOD, I mean, that would be even potentially increasing VMT in the system, and it would be probably a very expensive service for the customers too. So the short answer is no, the AMOD does not provide the service from the origin to the destination. It only fills those smaller first or last mile gap of the transit service.
And a follow-up question to that that I'm having is what factors are you using to determine areas to implement AMOD? So like how did you identify the case study area?
Great question. This case study was actually identified by local partners. The champions and the TAP members in the project were people from Duluth Transit Authority, DTA, and the MIC, I think MIC. I don't remember the acronym, but this is the Regional Planning Organization for the Duluth Superior Region. They identified this as a great case study. They thought, yes, this is something that we are dealing with. We know that there is inconvenient transit service there, and this could be a good case study. In that project, we did not look at the factors to determine other case studies, but this is actually a great follow-up question that any region can look at a few land use parameters, transit network parameters, and other things to identify a few locations where local AMOD can be applied as micro-transit kind of service to supplement the fixed route transit for their region.
Great, thank you. All right, and then moving on, we have a question from Michael, for Michael. Were there any inconsistencies between the streetlight and Strava data that made them hard to combine within the estimation framework?
Oh yeah, definitely. There were places where like the Strava just like ignored certain days, or like there was missing data for like certain days of the year, and then obviously Streetlight didn't have that. And then Streetlight, of course, like it's the data source is totally different. So it's hard to prove an inconsistency in Streetlight and Strava, because Streetlight's saying people traveling from out of origin and people traveling to a destination versus a link volume like Strava. But there should be some inconsistencies there in the network structure in terms of like people traveling that don't show up in Strava, just because Strava is not counting everyone. It's just counting people using the Strava app. And that's kind of exactly why we need this complicated model to try to minimize the error after combining these different data sources because of those inconsistencies.
And a follow-up to that, so like apps like Strava is geared towards more able-bodied people, kind of fitness enthusiasts. So are there other methodologies that we can use to kind of account for less represented populations? So, people with disabilities or older adults and like young children, and have them represented in this data set.
It's hard. I think like if you knew the relative adjustment, like if you knew that like the Strava users were like say 20% of the population, you could intuitively just want to multiply everything by 5, right? But the problem is that it's very localized, where like the different areas of the metro area are going to have different numbers of Strava users, and especially like where the Strava users are going to, like where they might take more recreational routes. So it's really hard to come up with a methodology without having good data, and the data is what we lack.
Okay. Thank you. All right. Just want to make sure I get everyone's questions here. So this is for Renee and Mark, a question from Amy. For the bike ped counts, did you notice any consistent geographical patterns in modeled versus observed counts? I think in places where there are likely to be more bike ped counts, such as urban areas or near university parks, the model counts are more accurate. Can you start to develop a measure of error so you have a sense of data accuracy at any single location? It is also in the Q&A chat if you would like to read it for yourself.
I'm curious if that question's for Michael, or is that for us?
Yeah, I think that might be a Michael question and not an us question.
Oh, is it?
Yeah, that's what I had intended for Michael.
Okay, sorry.
I didn't direct it though very well. Sorry.
Yeah, that is for you, Michael. Mhm.
Sorry, can you repeat that? I didn't realize that was for me, so I wasn't.
Yeah. Yep. So, Amy, feel free to come off of mute and ask your question if you'd like. I'll give you a moment. If not, I can repeat it. Okay. Yes.
Yeah, can you hear me? Yeah. So I know when you did the observing and then comparing that with the calculated or the modeled counts, did you do any sort of like variation in geography to try to understand, like how different locations might be more consistent with the modeled data versus the observed data? And just wondering if you could get to some sort of like estimation of accuracy, or like a margin of error that you could assign to any singular location to have an idea of how accurate that data could be at any point in the model.
Yeah, great question. We did try to choose a variety of locations in terms of like different bike trails as well as like suburban versus urban. We didn't have enough sensors and manpower to really have much of like a ton of locations. Like we had like one portable sensor moving around, and then we had like someone who was going out and counting things. So that obviously takes a lot of manual time. So I don't think I have like good data on geographic patterns of like errors, just because I don't think we have that many good locations to extrapolate from. But that's a really interesting question that I wish we had been able to look at.
Right. Thank you, Amy. Thanks, Michael.
Yeah, thanks. Thank you.
Mm-hmm. Okay. And now from Bruce, and I believe this is for either Mark and Renee, asking about motorbikes. And Bruce, correct me if I'm wrong about that. In what context is MnDOT thinking about motorbikes, high speed, non-registered, driven by teens, and not licensed?
Yeah, thanks for the question. Our specific research did not focus on e-motorbikes. We didn't look at that granular of a level. We were more focused on just non-motorized. So we would have looked at all bicycle types, so not focused on any specific category. Thanks.
And then a question from Matthew, going back to AMOD. Could you see AMOD serving as a safe routes to school tool in areas where busy roadways, difficult crossings, or other barriers limit the ability of children to safely walk or bike to school?
I think that's a really good point, and I would say yes. Probably the short answer is yes. I think there are more nuances of having AMOT serving children, and there are things that are really not in my area of expertise. For example, the human factor aspect of it, children interacting with autonomous vehicles without an adult supervising and things like that. But from the transportation planning perspective, if we can get the technology serving this purpose, I think it would be a great opportunity for providing safe ride to children to school. And this is very similar to the case that we studied. We had the case that people get off the bus, have to cross multiple streets and a highway to get to the final destination, a store or a shopping mall, and this is a safety risk to them. and we provide the AMOD from the bus stop directly to the curbside of that store. That provides a safer transportation for them. And in the case of a safe route to school, I think pretty much the same purpose. And I would say, yes, this is a great opportunity to explore. But again, the technology part is not my area of expertise. The human factor, the interaction with the vehicles without an adult supervision, I don't have an answer for that part of it.
And yes, Matthew, I see your hand raised. Mm-hmm. Do you have a question?
Oh, sorry. I was just I was going to give a thumbs up. Thank you for the response. And I guess I do. Now that I think about it, I do have another question. Wondering about the cost of those, the technology and the actual vehicles. Would that be cost prohibitive for a city to say target 4 or 5 of those for a continuous safe routes type of use like that?
Yes, thanks, Matthew, for asking this great question and then follow-up question. In terms of the cost, so full autonomous vehicles that would not need a driver, there are multiple options on the market, but I don't think the cost has converged to a stable, market-driven cost yet. But in the near future, we may see those costs getting more reasonable. But based on a study that was conducted in Switzerland a few years ago, they looked at the cost of basically the cost of serving a passenger mile by autonomous vehicles, taxi, buses, and personal vehicles, and other modes. And the conclusion was that autonomous taxis or autonomous MODs can be much more cost effective than human-driven vehicles, because primarily the human value of time or the driver's salary, which is a bigger part of the cost, will be eliminated. And even though the vehicles themselves are a little bit more expensive than the traditional vehicles, the net amount will be more cost effective with autonomous technology. I'm happy to share that paper with you if you're interested in looking at that.
Yes, that would be great. Thank you.
Sure, I will do that. I have if there's no other question, I have another follow-up answer to one of other questions.
Yes.
Do we have time for that?
Yep, we have time. Yep.
I think it was a question by Esther about the percentage of vehicles being in maintenance. And I said, no, our calculations did not account for that. But I'd like to mention that in a follow-up study that we conducted after this project, we looked at the autonomous mobility on demand system with electric vehicles. And with electric vehicles, there's a limited range. And therefore, at any point in time, some of the vehicles may go back to charging a station to get recharged. And that takes some time from the service of these vehicles. And we calculated the percentage of more vehicles that we need to have enough vehicles in service and enough backup in charging so that they can be replaced. They can replace those in-service vehicles. Again, we have calculations for that. Again, I'm happy to provide that if there is interest in that.
Thank you. So we are at time, but we do have one final question from Kessa. I know she put this in here earlier. This is for you, Michael. If I understood correctly, you were setting a minimum floor for ped and bike usage. Did you have any concerns with defending them when using them to justify which streets need more high-quality facilities?
That's actually interesting, because that's a project I'm working on right now, which is how do you use the data to determine where to build facilities. But in terms of the completed project, I haven't encountered any issues using those numbers to justify building infrastructure. But I'd also say partly that might just be because it was relatively recent, like completed like 1.5-ish years ago, so it may just not be having enough visibility or usage yet.
Great. Well, thanks, Kessa, for the question. Thank you, Michael. So we are at time, and this is the end of our webinar today. I want to give a huge thank you to Ali Reza, Michael, Mark, and Renee for your fantastic presentations and for your continuous efforts to increase safety in Minnesota's transportation systems. This webinar is recorded, and so you can always review at a later time, and we will send you all the information in a follow-up email. So thank you all.
Thank you.
Thank you.
Thank you.
Thank you.